let's get the boring stuff out of the way first. I'm a Microsoft employee. The views shared in this video are mine. I will use illustrations to simplify some of the more complex topics in the hope that they become more understandable. The video is not monetized and it's no way sponsored or endorsed by any people or organizations. I say people because I'm pretty sure that my dog would be happy to endorse this video for me. It's simply me talking about something close to my heart and that I work with often, and I've noticed the same kind of questions popping up time after time. I decided to create this video and future videos as a way to help and be able to point to a place to get some more information and clarification. And I really do hope that this video helps you. A typical database engine has 4 components that it uses to execute a query, as fast as these components will allow. They form the bottleneck in any database system, and we want to make them as fast as possible, but everything comes at a cost. The first and most important part of any database or data warehouse system is the central processing unit, CPU for short, or simply processor, and it's the main chip in a computer responsible for carrying out all the tasks. It is responsible for telling all the components in a machine what to do. In fact, CPUs exist in many types of devices apart from computers. If something can run a program, chances are that it will have a CPU. Your database server probably has multiple CPUs with multiple cores, or a single CPU with multiple cores. A core is a CPU, which also allows the processor to do more work for less space in the server. To be honest, in this discussion, it isn't important which configuration your server has. Just be aware that you will have multiple cores on a production system. You also get GPUs or graphical processing units, which isn't really used in database systems yet. Next up, and also very important, is memory or RAM. Memory should normally be the fastest data access point in your server. The database engine will use memory to hold previously selected records or keep some information required for fast access when it gets to the CPU for processing. Typically, any database engine will use the majority of the memory available to the system, within limits, or, if you miss the class, without limits, and that might cause you some issues on your operating system and with other programs. In SQL Server, as well as in Azure Synapse Dedicated Pools, any record needed for query must be in memory to be used. No record is used directly from the disk of the system at all, ever. Thirdly, we have I/O, or input-output, and this is how we get data into and out of the system. In most cases, when we say I/O, we mean the performance levels of the disk or the storage system, sometimes also referred to as the storage subsystem, on the database server. This is where data is stored permanently. It could either be local or remote storage. It is more typical to see remote storage for data or local storage for the temporary database, to have different I/O paths for this so that we can get better bandwidth out of the server. Any record that is needed for query that is not located in memory must be read from disk and placed in memory for the query to be processed. In terms of reading from memory, this is magnitude slower to do and should be very optimized in database systems. Any new or changed records must also be persisted back to the permanent storage. All of these processes makes use of the available bandwidth to the disks, or simply called disk I/O. I/O, as a concept, would also include the networking components. Last, we have 10TB. Typically, this wouldn't be called out as something as part of an SMP system, but I wanted to call it out as a big difference when we compare an MPP system to an SMP system. When we talk about I/O, the temporary database, or 10TB, makes up a part of the I/O requirements of the system and has an impact in queries and the performance levels of the database server. So much so that if there's a requirement on the 10TB, like large temporary tables, sorts, or what's called 10TB spools, it can and will have an impact on performance. I think that 10TB is important for performance and comparison reasons and added it into this comparison. These components are what delivers the raw performance to the database engine. There are other places that we can get performance, like query tuning, but to compare SMP and MPP, we only want to look at the hardware as a fair comparison. An SMP system is only a single server that can be used to get performance. Drawback for this is that adding more CPU cores, as an example going from 4 to 8, will not give you a 100% performance improvement. And then jumping from 4 to 32 will not give you an 800% performance improvement. There are diminishing returns to adding more cores. There is no argument that you won't see an improvement going from 4 to 32. it'll give you a solid performance improvement, but this performance improvement will quickly taper off as your core counts go up. As an example, jumping from 96 to 128 cores will not see a big improvement as on a system going from 4 to 32. There are other bottlenecks on a typical system that would have to be considered. I'm generalizing a bit, of course. It is also important to note that there is typically a single bus or communication channel for all of the components in the server, and that might become an important bottleneck as we try to squeeze more and more performance out of the database system. An MPP, or massively parallel processing system, like Azure Synapse Dedicated Pools, is when we have nodes in the same concept as a normal SMP system, but we use multiple nodes to get around the inherent limitations of a single system. We solve the scaling problem of an SMP system by adding nodes which have their own bus, CPU, memory, I/O, and tempDB. Adding an additional node will therefore give us a significant performance boost as opposed to adding a CPU into an SMP system. The nodes have local and remote storage like an SMP system, and the remote disks will be attached to the nodes to facilitate data movement in the nodes as well as between nodes, which in Azure Synapse Dedicated Pools is termed near instantaneous data movement. We won't go into details as to how the disks attach or the number of CPUs in the node, as this is guaranteed to change as new hardware becomes available. And to be honest, this doesn't really matter if you think about a cloud service. Wanting to know the number of CPUs or how the disks function is very much an on-premises way of thinking that doesn't fit in the cloud world. I want to add that you shouldn't sweat it if you feel a little bit lost here. You will see some illustrations to explain this in detail in a couple of minutes, and that should hopefully clear it up. The collection of nodes or servers with the same components as an SMP database server work collectively to satisfy the requirements of the query being sent to it. Think of it as if we're dividing a big task into smaller segments. But for this to happen, we need something to split this big task into smaller tasks. This component is called the control node, and the other nodes that does the work are called the compute nodes. Azure Synapse Dedicated Pools can scale from very small to very large. I'll take you through this in detail in a couple of minutes. But back to the control node. This is used to split up the query into smaller pieces, and it sends it to the compute nodes, who in turn does the work and return the results to the control node to fulfill the query. All simple stuff, but there are some caveats that I'll jump into in a lot of details as we go along. Let's look at the simple animation of SMP versus MPP. We have a guy that's busy cleaning a doctor's office, kind of like having a processor in an SMP system. We want the office to be cleaned faster, and we add more people to do this. In essence, adding more processors, which will give us better performance and allow us to get through the task of cleaning the office much faster. With obviously the exception of the guy with a mop and a bucket, and he's mopping the carpet, but let's ignore him and his wild ways. The amount of people is all fine and well for an office, but what if we had to clean a whole building? This would be very much less efficient, but still doable. But let's imagine a stadium. Now this group of people are woefully too few for the task, and this would be a very apt description of the differences between an SMP and an MPP system, as the stadium or building would be cleaned much more efficiently if we had multiple teams doing the work with someone overseeing the teams, just like our control node. But, and this is a very big but, an MPP system is not the solution for everything. When you want to do a singular insert or delete or run a transactional workload, then an MPP is not the best place to be. As with this example, having a single dentist is a good idea, but adding more dentists is not going to make the task of fixing or examining the little girl's teeth faster or better, and adding even more dentists will slow down the process even more. Just imagine how they will run into each other trying to get a look into her mouth. Keep this in mind when you think about what kind of system to use for your data patterns. DW what, you say? Remember when I said that we can add additional nodes and that we can scale from very small to very large, and that the amount of CPUs and such doesn't mean much and can and will change with different hardware? Well, that means that another measure must be used to give us an indication of how much performance we are getting out of our dedicated pool, and this is simply called data warehouse units, or DWUs for short. Here you see a node. The node has processors, memory, I/O in the form of disk and network, and tempDB. The node that we are looking at is the smallest available. It's 100 DWU. which has 60 gigabytes of memory and will host 60 distributions. More on distributions and how they work a little bit later in the video. Next, we have a 200DWU, which has 120 gigabytes of memory and hosts 60 distributions. So essentially twice as powerful as a 100DWU node. Next is a 300DWU, which has 180 gigabytes of memory and hosts 60 distributions. In essence, 3 times as powerful as a 100DWU node. Next is, as you might have guessed, a 400DWU node. It has 240 gigabytes of memory and hosts 60 distributions. It is 4 times as powerful as a 100DWU node. And last but not least, in a single node, is the 500DWU node. It has 300 gigabytes of memory and hosts 60 distributions. It is 5 times as powerful as a 100DWU node. These single nodes are not yet MPP, they're only a single node. Microsoft expects that all production systems will be at least a 1000 DWU unit, as this is the first place where you get more than one node, so a true MPP. As you've surmised, each 100 DWU increase adds 60 gigabytes of memory to the node. We just spoke about DWUs, and now we will look at the distributions. Remember that there are always 60 distributions, which means that a single node, the 100, 200, 300, 400, and 500 DWU, would host all of these distributions, 60 in total. So what are distributions? Distributions are singular databases that hold the information for your data warehouse. If we use a round-robin distribution, a record will be sent to a distribution, and then the next record will be sent to the next distribution, and so on and so forth. I will show the concept for this and hash distribution in a bit. Essentially, it is the place where your data is hosted and retrieved to satisfy every query. Each node, as it goes up in size, right up to 500 DWU, simply get more resources, but continue to host all 60 distributions. And fun fact, if you've ever wondered about the DWU sizes and amount of node counts for a dedicated pool, it's simply the number of nodes where 60 can be divided in as a whole number. Here's a 1000 DWU. You will note that it has 2 nodes and each node will host 30 distributions. A 1500 DWU will have 3 nodes and each node will host 20 distributions. A 2000 DWU system has 4 nodes and each node will host 15 distributions. A 2500 DWU system has 5 nodes and each node will host 12 distributions. A 3000 DWU system has 6 nodes and each node will host 10 distributions. A 5000 DWU system has 10 nodes and each node will host 6 distributions. A 6000 DWU system has 12 nodes and each node will host 5 distributions. A 7500 DWU system has 50 nodes and each node will host 4 distributions. A 10,000 DWU system has 20 nodes and each node will host 3 distributions. A 15,000 DWU system has 30 nodes and each node will host 2 distributions. And last is the big beast, a 30,000 DWU system, which has 60 nodes and each node will host 1 distribution. Now that we've seen nodes and distributions and how they connect to each other, let's talk about actual table distribution, how we distribute the data to a table. We'll start by looking at round robin. This is the one you're going to select if you're a fan of bad performance or a lot of data movement. Round robin is typically used in 2 situations. 1, for staging or loading tables, and number 2, if you don't see a discernible key or way to distribute your data evenly over the distributions themselves. We'll go into a little bit more detail when we talk about hash-based distribution as to how we would distribute these tables. The reason for using round-robin tables in staging and loading tables is purely because it's really fast in loading data. The one thing that you don't want to do with round-robin tables is join onto other tables. When you do that, you'll see a lot of movement and it's going to slow down your query massively. Be careful of this. I'm going to use an illustration to show you the examples. I'm going to be using apples and oranges. And yeah, as you guess, we're going to be comparing apples to oranges. The one thing that I do want to highlight is that although round robin gives you even distribution, this doesn't count if you have a low row count, right? You need to have an X amount of rows for this distribution to happen. You'll see tables skew with too little rows. In the animation, you'll see that I'll only use 6 distributions. This is just to make the explanation a little bit easier to do. Just keep in the back of your mind that a dedicated pool always has 60 distributions. The first orange is going to go into container 5. This is a random selection. This is what happens in a dedicated pool as well. There's random selection over the distribution where round robin will start. The next orange will go into container 6. And then it'll go to container 1 because it's reached the end of the list of containers available to it. Next will be container 2, and so on and so forth, until it reaches the end of the amount of rows that it has to add. When we add new rows again to this table, it'll continue where it left off. So if the previous container was container 4, then it'll place the next row into container 5. And now we'll have our apples appearing. This is obviously a second table, and we'll be joining between the oranges and the apples. The first apple will go into container 3, and the next one will go to container 4, and then it'll go to container 5, and then 6, and start over at 1 again, just like the oranges. And then the apples will be added one after another into the containers. Same principle as the oranges, it'll continue on where it left off the last time. Now we need to do a query. The query is going to be simple. I want to take the oranges and I want to take the apples and compare them. I want to find relatively between the two which one has the biggest apple and which one has the biggest orange relative to each other. Now the problem for round robin in doing this is that I would need to take a copy of every apple and every orange and make sure it's on each node. So let's assume that container 1 and container 2 is node 1, container 3 and container 4 is node 2, container 5 and container 6 would be node 3. That means that I'm going to move all of the apples in container 1 and 2, node 1, to node 2 as well as node 3. I would then have to take all of the apples and oranges from container 3 and 4, which is sitting on node 2, and I would move them to node 1 and then node 3 as well. And the same would happen with node 3. All of the apples and oranges must be copied over to node 2 and node 1. This copy is going to make use of the DMS, or the data movement service. This is what we use to move data between nodes. This data will be stored in the tempdb, and that's where we're going to do that comparison. So let me show you roughly how it's going to look. All of the apples and oranges from node 1 will be copied to node 2 and then node 3. All of the apples and oranges from node 2 will be copied to node 1 and then node 3. All of the oranges from node 3 will be copied to node 1 and node 2. Now you can see that we can do the comparison here, but we've had tons of data movement happening. And this is what causes the slow performance of round robin tables. The next table distribution that we're going to talk about is hash-based table distribution. This is meant for larger tables, so think about fact tables, so tables with millions and billions of rows. These are going to be the tables that will form part of the joins. We used to only have single column distribution to distribute these tables, but luckily now we have multi-column distribution, and that'll avoid a table skew to a very large extent. Let's use an example to explain these tables. As I might have a report that'll join onto this table, let's say sales for the city. So I'm going to distribute the customers based on city. With single distribution, I would have to take all of the queries into account that I would have to execute against this table. I would then have to make a decision around this distribution. And I would have to pay a price should I execute a query that doesn't follow the distribution of this table. I would then see massive amounts of data movement maybe happen. Luckily, we have multi-column distribution now, which makes distributing this data a lot easier to do and would avoid data movement. But let's for a moment imagine that I've got another query. Let's gonna run against this sales-based table, and I want to know which products were bought. Now the distribution isn't based on product, it's based on city. I would have to join the sales table to the product table, and they are not distributed in the same way. I would see a very large shuffle move happen to move the data into the correct node so I can actually do the query. We would simply have to eat the cost of the query for that. There was nothing we could do. Now let's also imagine that we wanted to know in which age groups our customers were. Once again, table isn't distributed for this, and therefore we're going to have shuffle movement happening, and I'm simply once again going to have to eat the cost of this query. But like I said before, luckily multi-column distribution has come around, and it'll save us in all of these cases. So we'll see much less data movement. Okay, time to look at an animation again. You'll note that once again we have 6 containers or distributions, but this time we've got a scale, and next to the scale is a board. The board's going to tell us into which distribution or into which container the specific fruit should go based on what type of fruit it is, as well as its weight. Let's start with an apple. It's going to go onto the scale, and this scale uses black magic and artificial intelligence to know which fruit it has. In this case, it's a red apple, and it weighs 160 grams. The scale then determines, based on the board next to it, that an apple with a weight of 160 grams should go into container 1. Off it goes. Another apple appears, and it's weighed by the scale, same as the first apple. It's 60 grams, and its hashed value means that it'll go to container 6. And off it goes. Another apple appears. It's 94 grams, and it's going to go to container 1, based on the hash that it calculated. One more. It's 83 grams, and it's going to go to container 4. A large apple appears. It's 151 grams, and it's going to go to container 1. We're going to have a bunch more apples appear, and they're going to be hashed and then placed into the correct and corresponding containers. Please take into account, although the apples and oranges are coming at different times, this is not how it would work on a dedicated pool. These apples and these oranges, they would come as they were entered into the system, not separated at all. A wild orange appears. Finally. It's going to go onto the magical scale, it's going to be hashed, and the correct container is going to be selected. In this case, it's 94 grams, and it'll go to container 3. On the next one, it's 78 grams, and it's going to go to container 5. One more. It's going to go to container 3 based on its weight and the type it is. Now we're going to have a bunch of oranges appear. They're going to be weighed, the hash calculated, and then they're going to be distributed to the correct containers. Now that we've placed all of the fruit, we can do the same query we did in the round robin. You'll note that we have no data movement. It's just going to select the apples and the oranges that are the largest in container 1, and then it will do the comparison there. So no shuffle move. You might be asking yourself, how does hashing happen? Let me explain it with an animation. Here we have Peter sitting. He decides that he needs to add an orange to the dedicated pool, which is obviously over to the far right. The orange is exactly 60 grams, as you can see, and it needs to get into a distribution in the dedicated pool and go and live happily with its other 60 gram orange friends. Peter enters the orange, and it flies up to the closest Azure data center. It gets there and it's scanned by the hash function. Here it looks, well, to me at least, impressive, but it's fairly simplistic. It takes a value and its data type and converts it into a hash value. This is obviously a deterministic hash, which simply means that it's going to return the same hash value for the same value and data type. In this case, the 60 gram orange gets a hash of 42. No, not really. A hash wouldn't be that simple. The hash here is a bunch of letters and numbers in it, and it also defines to which distribution this orange will go to. And this means that the orange can now happily go to its container. All good and well. But let's take a closer look at the hash function and send some other values through to it. And let's then have a look at what it comes up with. We're going to use a value of 5, and this is going to be the distribution column for this table. First, we send an integer type with a value of 5 through. We see that the hash for an integer with a value of 5 is CPW503CF, and it will go to distribution 21. This means that for every integer with a value of 5, we will get exactly the same hash value, and it will always go to distribution 21. Next, we're going to send a big integer type through with a value of 5. Interesting enough, we get a completely different hash value. In this case, U93VYO4T, and a distribution of 56. Just like the integer with a value of 5 will always get the same hash, the big integer with a value of 5 will always get the same hash. Now, this is almost guaranteed not to go to the same place that the integer with a value of 5 will go to. Keep this in mind. So let's send an varchar of the size of 25 through the hashing mechanism. It's also got a value of 5, so let's see what happens in the hashing function. We'll send it through, and we see that it has a hash of DDTLC5TT and a distribution of 4. Once again, this will always be the hash and the distribution that an invarchar 25 will go to with a value of 5. Now let's send an invarchar with the size of 24 with a value of 5 through the hashing mechanism. What do you know? Completely different hash, as expected. Now this one gives us a hash of R4013DPZ with distribution 34. Once again, completely different, but not unexpected at all. And this is always a deterministic hash. Obviously, the hashes and the distributions that I used here is fictional, and just an example. We can be assured that even if we send through the same value on a different data type, that they will not end up on the same distribution. This is important. I see this fairly often, where people will have int and big int or tiny int, and they assign the same value to them and expect them to be on the same distributions. This is not going to happen. Must be the same data type. And take into account that if you cast the value to another data type, you might run into this very same problem. To wrap it up, we're going to talk about indexes. There are 3 types of indexes that we're going to talk about. Those are primary table indexes. First one is clustered index. Second one is a heap, which is actually a lack of an index. And then the third one would be clustered column store indexes, or CCI, as they are referred to. There's also non-clustered indexes. I'll touch on them briefly, but they are not primary table indexes. Once again, I'm going to explain all of this with animations. It won't be apples and oranges this time. I'll use postal services with a housing system. I'm pretty sure we're all tired of seeing falling apples and oranges, so let's try something new. For this animation, we're going to use a map. You'll see the map will open up. We'll be zooming in. And this is in essence what we'll be using for this animation and the explanation itself. We're going to use this map, and I'll show you how post people will deliver mail based on the cluster that I'll be describing. I'll be talking about clustered indexes now. So you can see we've got a street. The street has houses. It's numbered from 1 to 12. And for a clustered index, the values are sorted. It's not a physical sort, so it's not like it's sorted on the hard disk at all. When we look at this kind of index or the delivery that we're going to use here, what we'll see is if I've got to deliver from house 1, 4, 8, 10, and 12, then I can build a good plan to deliver to that house. I can drive right up to the house, the first one being 1, then I'll move to 4, then I'll move to 8, and then I'll take a route to 10, and from there I'm going to move to 12. Very efficient. I can plan this route, and this is normally how things would happen in our world. The mail service would plan this, and then a person would go along and deliver the mail. Quite simple, straightforward. Now let's talk about heaps. Heap has absolutely no index that describes how the data should be organized. When a row gets added, in this case it'll be a person moving into the house. That person will go into the first available and open house. If we then have another person moving in, you'll just get the next open and available house, and so on and so forth. But we can also have people that will move out, or people that move to another house. In a heap, an X amount of space is allocated to a page. Now if this page gets too big for where it is, you'll get a forwarded row, and I'll show you how a forwarded row is going to look when we deliver the post. Now, this index type or lack of index type makes it really difficult to plan ahead, right? To plan your route. It means the post person has to stop at every house and check, hey, is this person living here that I need to deliver mail to? Not efficient at all. And what you're going to see is we're going to use the same one. We're going to deliver mail to 1, 4, 8, 10, and 12 again, but on a heap. And one of these people have moved, and therefore we've got to go deliver the mail to where they've moved to, and this is going to slow us down. You'll see it in the animation. So let's have a look at the animation. Luckily we've got house 1 first, and that's an easy one. We would have stopped there anyway. Now we're stopping in house 2, now at 3, now at 4, and we find the next row that we wanted. So luckily we can deliver the mail there. And we go to house 5, then we go to house 6, then we go to house 7. Now we head off to house number 8. And what do you know? The person doesn't live there anymore. So we're going to go head off and look for this person. We found the forwarding address, and that means I can go to where they live, but it's not going to be on my route, and I've got to head off and go do this, right? So I head off and I go do this, and we wait. And then we come back, then I'll check house 9, I'll check house 10, I have mail to be delivered there, I'll check house 11, and then I'll check house 12, and our mail is done being delivered. Hopefully you see how inefficient it is to use heaps. The benefit though, they are really fast for insert. So if I just want to dump a lot of information into a table, heaps are amazing at it. There's no index maintenance whatsoever. I just find the next available house or next open page, and I plonk my row in there, or I put my family in there. Easy peasy, but not really good for any kind of querying. Let's talk about cluster column store indexes. This index type is very different from the ones we've spoken about previously. The previous ones were row stores or lack of a index. With a clustered column store index, we have a compressed columnar store. Now, the columnar idea is that if I have a bunch of rows and I have a similar value in these rows, so imagine I've got millions and billions of rows, we're going to have a repeat in these columns, and that means that I can put these values together. I can find the ones that match. I can compress them, have a pointer to it, and then I can have a really good index type where I don't take up as much space as a row store, hence the compression. And then I can also have a really fast table scan over a large amount of data. The problem though with column store indexes is that they are read-only. Now what we do to get around this read-only problem is we have what's called a delta store. So if there's an update to a row, or if there's a deletion of a row, we will place it into the delta store. And the delta store will then be used as kind of a journal versus the columnar store. So I will read the values from the columnar store that I want. I will compare it to the delta store, and then I would either do the modification, so in terms of like an update, or otherwise remove rows in terms of a delete. Now you can imagine checking this delta store would be slower if there was a lot of entries in the delta store. Typically you want to keep the entries in your delta store as low as possible, so you do index maintenance to compress them and to update your row store itself. An additional great thing about the columnar store is that there is probably about 8 times compression. So you're going to save a lot of space using this type. If you do a large amount of table scans over a table, then this column store is going to help you with doing that. It's going to be fast and efficient at scanning big tables. Right, so in our example, what's now going to happen is we have a bunch of mail to deliver. We're going to replace a couple of the houses with a high-rise building, and this is going to represent our clustered column store. The mail delivery person will drive as normal, not going to stop at any of the houses except for the high-rises. There's going to be 3 of them, and when the mail delivery person gets to that house, it's going to stop, move in, deliver the mail. The person who works in the lobby of that high-rise is going to accept the mail, make sure that the mail is meant for the people in there, and that's it. Then the mail person can move along. And in this way, we have a very efficient way of getting to our data, or in this example, just purely delivering mail. So as you can see, a supremely efficient way of delivering mail or reading data. And in our example, you'll see we're just going to drive up to the first high-rise, deliver the mail, move to the second high-rise, deliver the mail, move to the third high-rise, deliver the mail, and that's it. We're done. And so we come to the end. As all things must end, so must this video. We've talked about a lot of subjects. We've covered a lot of stuff in a dedicated pool. I hope some of this is insightful and helps you with understanding some of the concepts. And like I said in the beginning, I just wanted to point out and have one place where I can point to say, let's talk about indexes, let's talk about table distribution and so forth. You'll note that there are other videos for Azure Synapse Dedicated Pools that I'm making. Some of them are loading data as well as checking performance when we have different distribution types and all of these good things. So if that interests you, please have a look at the other videos.